Okay, we better start then. Good afternoon, and thank you very much for finding time to join us again. This is the fourth webinar in the NIWA and SPC Learning Exchange series of webinars. As a reminder, the goals of the webinar series are to provide a forum for exchange of learning and expertise that underpins the work of our two organizations, and to ensure that we create space for further collaboration in the field of development in the Pacific. Both organizations, NIWA and SPC, base their work on science and in part on use of scientific computing that we promote in this series. Before we start, a few housekeeping matters. The webinar will last for about 60 minutes. 45 for presentation and 10 to 15 for questions and answers. The event is recorded and the recording will be published on the SPC YouTube channel, and the link to the recording will be made available on the SPC website. Please let me know if you object to that. Please mute your microphone and close your camera to minimize bandwidth needs. We have colleagues from SUA connecting and they work from home due to their COVID situation there, and their bandwidth is limited. Please hold your questions until the questions and answers time, which is after the presentation. However, you are welcome to ask your question in a chat box at any time. This webinar will focus on climate change topic, extreme weather events in particular. It will help us understand to what extent extreme weather events can be attributed to human climate influence and how we might expect these events to play out in the future. The presenters today are climate scientists Dr. Dáithí Stone and Dr. Suzanne Rosier. Together, they bring vast experience from working in the UK, US, Canada, Latvia, and South Africa, among other places. Without further ado, I hand over to Dáithí and Suzanne, and I will stop sharing my screen too. Okay. Over to you.
I'll just start. Hi, I'm Dáithí, and you can see Suzanne, Sue there. Just have our videos on for a moment so you can see who we are. On the note of extreme weather, I'm working from home this morning, or well today, because we've had a lot of rain here and there was a landslip covered the train tracks and a train is derailed. So I can't get into Wellington right now on my usual commute. Sue, can you get the slides up? Sue will do most of the talking today, so it makes sense that she shares the slides. I'm afraid I've missed the talk so far. It's a pity. I would have liked to have, and it's usually a good time for me. It's just the past few weeks have not worked. There we go. Got it. So I think some of the stuff Sue's actually going to talk about attribution and how to use a certain climate modeling setup for that. I'll just provide a little bit of context on that. And some of this will overlap with what, probably, hopefully, with what Johnny Williams spoke about a couple of weeks ago, I think. Sue, next slide, please.
Sure.
But we're kind of interested in the next one. Yeah.
Sorry.
There we go. What we're interested in doing is creating climate information, and that's one of the things that NIWA focuses on, and in particular under the context of climate change. So what Sue will be talking about today is really about understanding the present and the very near past, but some of it is about understanding the past, and some of it is about understanding possible futures. And last week, or 2 weeks ago, I guess, Johnny talked to you about the New Zealand Earth System model. So these are very complicated models, I guess the most complicated models of the climate or sort of weather system that we have. They're they deal with not just with the atmosphere, but with the ocean, with chemistry in the ocean and the atmosphere, with land processes, with ecosystems, with ice sheets, all these sorts of things. So they're very useful for understanding particularly kind of global changes on a timescale of centuries. And so if we keep on emitting greenhouse gases, what will the world look like? But for other purposes, we might be interested in other topics related to climate change, closer to home right now. Maybe it's some sort of conditional question. And so we actually have a number of different tools that we use to consider these things. So on the top left, we have the global Earth system models that Johnny talked about 2 weeks ago. We have global atmospheric models, which are very similar, except you take off the ocean, you take off the chemistry, you turn all of that off. And that means that you can run these things more quickly. And it means you can start focusing in more on fine scale details because you don't have to use all this computing to work out chemical processes and so on. And you can take this a step further and do dynamical and statistical downscaling. So this is a process where you use kind of a smaller, very regionalized version of that atmosphere model to focus on an area of the world, where you use statistical relationships. When the wind is blowing this way, we tend to get rain. Things like that to come down to an even finer scale. We also use weather forecast models or increasingly to understand climate change. So this in this particular plot here on the bottom right, this is a recent rainfall event that occurred in South Island of New Zealand, and it was a record event there. And so this is from a forecast of it, and what we're trying to do is look at how would that forecast have differed if we had not emitted greenhouse gases, say. And you could also do that looking towards the future. How might this event be different in a world that's a degree warmer than it is right now? And this is stuff that we do in collaboration with Met Service and Bodacre Scientific here in New Zealand. And then, of course, finally, over on the bottom left, and possibly most important, are the observations themselves. So these are the observations of that event in South Island. And you can see that the rainfall actually occurred in a very narrow area, the record rainfall in the foothills of the Southern Alp Mountains. And that was really what caused all the flooding and so on. So you want to be able to get down to a fine scale for this. Next slide, please, Sue. So you can use all of these tools separately, or you can use them in a sort of chain. And I see Peter Gibson and Steve Stewart are on the call. I'm not sure if Abba is as well, who run the regional projection effort within NIWA, which is predicting what the future will be like given certain possible scenarios of how global climate might change. And so we have the global Earth system models like NZESM, which predict how general properties will change throughout the world. And in the last the last phase of doing this, they use data from those models to drive global models, which could do the global atmospheric processes in better detail. And these were used to drive a very targeted model of how the weather changes over the New Zealand area. And then that was further used some statistical relationships to take the output of those simulations down to data that produces these things of a prediction of what rainfall might look like during the winter. In this case, in NIWA, a century, or in New Zealand, a century from now, and how that will have changed because of climate change. So this is kind of a chain of all of these different tools to produce information at a fairly refined scale. You can see in here that depending on which side of the mountains you're on, you can get a very different climate change response. On that note, I'll hand over to Sue to talk about a particular application we've been using this for. Sue?
Okay, thanks a lot, Dáithí. So for my part of this talk, I'm going to tell you about specifically about the Weather at Home project for the Australia and New Zealand region. And then I'll say briefly some of the things that we've used this regional climate modelling experiment for, which in this case is essentially the attribution question of the effect of human influence on the climate. And then in the final part, I wanted to tell you a little bit about an application of this sort of attribution information that we did for the New Zealand Treasury in recent years. So mostly I'm wanted to tell you about the Weather at Home project. And as I was thinking about this and essentially looking back over the history of the project, I realized just how many people there are to acknowledge here. Too many, don't worry, I'm not going to read all these out, but really loads of people have had an input into this. Weather at Home runs as part of climateprediction.net, which is based in Oxford. And for this part of the world, we developed it as a collaboration among the UK, Australia and New Zealand. So there really are very many people to thank here, and many funding bodies as well. Here's my attempt to simplify climateprediction.net. Sorry, something just popped up on my screen, distracting me. So Weather at Home runs as part of climateprediction.net, which is a distributed computing project that essentially relies entirely on volunteers for computing power. Personal computers, spare processing power on personal computers is what actually does the grunt work of computing climate models in this project. So about 20 years ago, a couple of very clever guys in a basement in Oxford figured out how to make a fully complex global climate model available to download to anyone in the world with a PC and an internet connection. It was the brainchild of Miles Allen in Oxford, and it was launched in 2003 with global climate models, and those have almost always to date been UK Met Office models. So, those are the experiments are prepared by Oxford, released to the general public. As I say, it relies entirely on generous volunteers. You can download one onto your computer. It should only use the spare processing power on your machine. It shouldn't interfere with anything that you're using your machine for. And then the results are uploaded to anywhere in the world. So climateprediction.net started originally with global climate models, and the amount of compute that's harnessed in this way is quite phenomenal. So there have literally been millions of model years simulated in this way. And the power of that really is that we can have much greater statistical confidence in the results than than scientists can normally hope to achieve. These are the sorts of models that scientists use, and usually can only hope to run maybe a few dozens of times at the most. So it's a very powerful experiment indeed. After it had been going for about 7 years, in 2010, CPDN launched Weather at Home, which is essentially, instead of just the global model, that global model now has embedded inside it a regional model, which is at higher resolution, so much more detailed than the global model. So in a sense, it's downscaling the coarser information in the global model. So that was a combination of increasing the resolution for a particular region so that we can understand more about more localized patterns, but still having this phenomenal resource and capability to run those many thousands of times, which will basically enable us to say something about how weather patterns are playing out. And one very obvious thing that this is very suited to, therefore, is looking at weather extremes, because if we can run our model thousands of times, then we can actually have a pretty good idea of, say, the 1 in 1,000 year weather event. We don't have to use Weather at Home for extremes, but it's a natural sort of focus, and that will certainly be the focus of what I'm going to say after this. So in 2014, we launched Weather at Home for this part of the world. So we call that Weather at Home ANZ. Oxford still put the experiments together and release them to the public, but the results are automatically uploaded to a server in Hobart, TPAC, Tasmanian Partnership for Advanced Computing. And they've been steadily receiving results for several years now. At the time we launched, we had about 1,000 New Zealand and 3,000 Australian participants. I haven't updated that figure for a while, but essentially there's a hard core of about 50,000 crunchers who routinely crunch these models. It's a phenomenal resource, and of course we're very, very grateful to the volunteers, and if anybody wants to take part, it's very easy. You can go to climateprediction.net or weatherathome.net and just sign up. So this is just a schematic. I think I've probably covered most of these things now, but here's a schematic of the 2 Met Office models that that are released to the public, and Weather at Home originally launched with just 3 regions, but ANZ was, I think, the 4th, and it was the first one to be launched remotely from the project base in Oxford. So that was neat. But since then, the project has gone on to model very many other regions of the world as well. This was simply my attempt to sort of locate some of the bits and pieces that go into it. I figured if I was going to try and show you where is involved, I might as well have a map of 2-meter temperature anomaly, but sorry if that's just confusing. But there's the project base in Oxford, and as I say, the UK Met Office is very involved because it's using their models. Melbourne and NIWA were very involved in creating it, and the server in Hobart stores about order 75 terabytes. It's a huge amount of data that we collect in this way. It's a phenomenal resource. Nessie and the HPCF here in Wellington have been fantastic about helping us store that and analyze a lot of it using the virtual labs. But of course, the actual crunching of the models is done by the volunteers. And after a few years of essentially doing it themselves at climateprediction.net, they decided to run Weather at Home under the BOINC platform, the Berkeley Open Infrastructure for Network Computing. So really a global effort, but of course, none of that would be possible without the volunteers, and every black dot on this map here shows you a location where somebody is volunteering their computer to crunch these models. So somebody pretty much in the four corners of the earth helping the project out in this way, although obviously it's you can see it tends to be concentrated in Europe and North America, but really volunteers everywhere pretty much. So this is the actual Weather at Home ANZ domain. It's at 50 kilometre resolution, so each one of these grid boxes is 50k square. By regional modelling standards, it's a pretty large domain, which does mean that we've had to, we've been a little bit limited in some of the output we can store. But under a new New Zealand government funded project, we do have plans underway to essentially create a version for New Zealand only, which will be exciting for us because it will mean we can store a lot more output, and it's going to be at higher resolution, so that will be at 25 kilometre resolution instead, so we look forward to that. I'm a bit of a stranger in the Pacific, forgive me, so this was a good geography lesson for me. I figured I could make out Samoa here, but not the Cook Islands, so hopefully that just gives you an idea of what it looks like in this model. And if you sign up to volunteer your computer to the project, whoops, sorry, then there's a very neat interactive graphic by means of which you can see the model that you're actually running on your machine, how it's evolving at the time. So there is, the project tries to give back something to the volunteers who want to engage a bit more, and there are very active discussion boards on the climateprediction.net website, whereby participants who want to get a bit more involved can. This is just a view of cloudiness in the Australia-New Zealand region. And here are a few more examples of the sorts of things that the participant can see when they run these models. And just the last bit about Weather at Home, just a reminder really about what New Zealand looks like. This is what the 50k grid essentially looks like in our model. So if you're interested in getting down to really very, very fine scales, or if you want to know how climate change is playing out literally in your backyard, then this isn't going to be the most useful tool. This would need to be further downscaled if you wanted to get to really, really fine scales. But as I've said, it's a trade-off between getting that fine resolution and having the statistical confidence. So what we have here is maybe not 5 by 5k resolution, but we do have a large amount of confidence in building up distributions such as the one you see here on the right, which is so what we have in each grid box is these many hundreds and thousands of runs which enable us to build up distributions of something like, for instance, here we have temperature. The green distribution is temperatures in the present day. The yellow is under a future that's 1.5 degrees warmer, and the red is in a 2-degree warmer future. And so we can, this is how those temperatures are distributed across these thousands of model runs, and that's a very great strength of the project, to be able to build up smooth distributions like this and know that sort of have that sort of statistical confidence. Hopefully you can also begin to appreciate how in the very tail of the distribution that the most extreme weather events, we can begin to have more confidence in assessing those, whilst recognizing, as I say, that everything's at this 50k resolution. Okay, on to the second part, which is essentially we have tended to focus with the weather at home experiments that we've done. There has tended to be a focus on attribution. That's not entirely everything, but that's what I thought I would talk about mostly today. Attribution, essentially what causes what. When we attribute something to something else, we're basically asking, you know, did that influence cause this? You can do an attribution study on any particular sort of climate forcing you like. With regards to climate, you need to use a model because it involves experimenting by isolating whichever forcing that you're interested in. But if we just say the word attribution, then with climate change, it's usually understood that we're talking about attributing changes to the human influence on the climate system. And that's what I'm talking about today. So this is just global mean, annual mean surface temperature anomaly up the side, and the anomaly from a baseline that's around here, 1880 to 1920. The black is observations, and the red is what we get if we force our models with all forcings. So we put everything into our model, which is as we believe it is, like greenhouse gas emissions and ozone aerosols, etc., etc. The blue is where we experiment and we take away the human influence. So we estimate how things, this is a measure of the world that might have been if humans hadn't altered the climate. And essentially this demonstrates the attribution issue. When we force our models with all forcings in the red, we get a very, very good fit to observations, especially over this latter half of the 20th century. But if we take away the human influence, then we fail completely to explain the warming over the second half of the 20th century. So it's been, these sorts of studies have been a major input into conclusions of such as the IPCC about how we can be pretty certain that human influence has been important in the warming that's been seen over the second half of the 20th century. But with regard to weather at home, what we're able to often interested in answering is the question of how did climate change or human influence alter extremes of weather? So more and more these days, as we get extreme weather events, and of course in particular very damaging ones, people are more and more asking the question, how was climate change to blame, or to what extent was climate change to blame? And with weather at home, we have a much better we have a good chance of assessing quite quantitatively how these types of events are changing. So this is just very briefly a study I did a little while ago as an example of a heat wave that happened in January 2018 as part of the 2017-18 there was a strong marine heat wave in the New Zealand region, and there was a heat wave on land as well. So in Dunedin, which is here, I decided to look at what the weather at home model was saying. So these are temperatures in that Dunedin region, and they're actually the January maximum of daily maximum temperatures. So temperature goes along the bottom here, and up the side is the number of models that had those sorts of temperatures. And as I've said, the power of the weather at home experiment is that we have so many of these fully self-consistent, fully crunched model runs that we can build up these distributions very, very nicely indeed. So here, the red is where we've just told the model to go away and compute the actual conditions. We've told the model everything that it needs to know, and what we force it with. We've said we think greenhouse gases were this and ozone was that, etc. The green is where we have taken away estimates of the human influence. And so you can see by eye that the distribution has shifted to warmer in the all forcings case. And it's generally the means, the averages of the two distributions have are about a degree apart, which lines up pretty much with what's been seen globally in terms of human-induced global warming. The black dotted line is the event as it was observed. So that's the actual temperature that was observed in Dunedin in that heat wave. And hopefully you can begin to appreciate how if we mark that on these distributions, we can begin to count how many temperatures warmer than that are in each of these red and green distributions. And that then that enables us to quantify to some extent how the chances of getting temperatures that high are changing between the two distributions. So how we can begin to be a bit more quantitative about how human influence is playing out in terms of extreme temperatures. So one measure of that difference is something we call the FAR, which you see over here to the right. That stands for fraction of attributable risk. I wasn't going to go too much into the maths of that, but essentially it's a way of estimating how the chances of observing extremes like this have changed between the human world and the world that might have been without human influence. And one way I don't know if this helps, but one way to visualize that is that we're looking at essentially two samples. The term fraction of attributable risk was actually borrowed initially. Miles Allen in Oxford around 2003 proposed that we borrow the term from epidemiology, and essentially the idea is that you're comparing two samples. For instance, what's the incidence of lung cancer in a sample of people who smoke and a sample who don't smoke, and how do the chances of getting lung cancer change between the two groups? And this fraction of attributable risk is one way of being a bit more quantitative about that. Okay, so on to the final part. How have we used, well, just one application of this sort of attribution information. A couple of years ago now, here in New Zealand, we did a report for the New Zealand Treasury. It was the idea of Dave Frame, who is at Victoria University in Wellington. And it evolved out of a conversation that Dave had with the Treasury about just beginning to think about the damage caused by extreme weather. And if we've got some sort of estimate of essentially the costs of those damages, then could we potentially use attribution information from large data sets like these model runs to begin to estimate how much of those costs are attributable to human influence on climate. The Treasury were very interested in the idea and were able to give us a very small budget to go away and begin to investigate this. It was a very small budget, which necessarily limited us in the approach we could take. So it was very much a pathfinder study. There are 1,000 criticisms you can make of it, and lots of ways in which it could be made more comprehensive. And that's something that we're actively investigating now via a New Zealand government MB funded project called Whakahura. We're essentially taking these ideas on. But essentially, I'm starting here with the results, really. This is what we found. So that that fraction of attributable risk, the FAR, Dave's idea was simply to, if you multiplied that fraction by the known costs of the damage caused by extreme weather, then you can get an estimate of the attributable costs. And so we did that for 12 floods and 2 droughts in the decade 07 to 2017. Part of the limitations of the study was that we limited ourselves to that decade, and we literally took a list of all the floods and droughts, particularly the floods. There were lots of these events, but we just limited ourselves. We ordered them from most expensive to least, and we picked the top 12 most expensive. These were the results. We got 140 million New Zealand dollars as the attributable part of the costs due to flooding. Droughts are an order of magnitude more expensive. We got 800 million as the attributable component there, so a total in the middle there of 940 million. This is simply to illustrate just how simple the approach was. Again, this fraction of attributable risk, if your fraction is a half, then that's essentially saying that half the probability of experiencing an extreme event in the world as it is now is due to human influence. So since this is a fraction, if you can multiply it by your total costs of the weather event to get the attributable, an estimate, a very ballpark estimate of the attributable costs. Just briefly, almost done, just to say that the actual damages, or the costs caused by these extreme weather events, were somewhat different for flooding and drought. For flooding, we took information from the Insurance Council of New Zealand, and they were insured losses only. That was private residential insurance, so there's quite a lot that's been neglected, public infrastructure, and the ongoing costs, like the full sort of cleanup costs and economic losses due to flooding events, were not included. So that's likely to be an underestimate. The drought, in the drought case, it's a much fuller picture of the costs, because we got it from modelling by the New Zealand Treasury, which compares years with and without drought. Because New Zealand depends such a lot on agriculture, the economic impacts of drought are really severe. These are generally, as I say, droughts are generally in the billions, whereas floods are generally in the millions. But we figured that these were both likely to be underestimates. And even though as climate scientists, we're often very aware of how approximate some of our numbers are, we also figured that actually possibly in this study, the climate science part of it wasn't nearly as uncertain actually as these estimates of the damages. So it's just a very broad brush approach, and a first ballpark estimate really, which is, as I say, being subject to ongoing refinement. So finally, I'm very nearly finished, but these, just to show you, really, these were our 12 costliest flooding events. There's that fraction of attributable risk. Again, it tended to be around 0.3, so about a third of the the probability of experiencing rainfall, the sort of rainfall and heavier as occurred in these cases, was around a third. And I probably also should have made clear that the attribution information came from the rainfall only in this study. And technically we should be taking it from the flood information. And again, one of the things that we're trying to do as we refine this work is to put large data sets of meteorological information into hydrological models and get better estimates of the actual flooding amounts. But this was done purely on the rainfall. So the average FAR was about a third. Here's the costs, ranging from about 90 million down to 15 for those top 12 Costliest. So the attributable costs, each of them multiplied by about a third, they came to 140 million in total. And our two droughts had a FAR of around 0.2, but since we're talking billions in terms of the total costs, that's still a pretty significant contribution of about 800 million to that decade. So I think that's about it. Thank you very much for tuning in, and don't hesitate, please, to get in touch. I think I can speak for Dáithí as well as myself. Do just drop us an email if you want to get in touch about anything, and I hope it's been of some interest.
Thank you very much, Susan. Thank you very much, Dáithí. We are now in the question and answers, or questions and answers part of the session. We welcome questions from the floor first, since we do not have any in the chat box. Any questions from the floor? If you do have a question, just unmute your microphone and let us know what the question is. Or otherwise, you can type the question in the chat box, and we just and we have one now, and says thank you. So the question is from Alexander Pletzer. The question is, thanks you. Do you see room for machine learning to future expand the number of simulations?
Yeah, thanks, Sue. Yeah.
Hello, Alex. Yes, certainly. I would like to know more about machine learning than I do, but from what I do understand of it, yes, certainly. I think something like Weather at Home probably provides a really rich sort of possibility for machine learning. Certainly, to you know, there's plenty to mine there. I would be I think, yes, it will never, of course, replace the fact that what's so useful about this sort of distributed computing approach is being able to compute model simulations that really are fully dynamically consistent, and my understanding is that you can't replace that aspect, but I'm certain that it would provide a really good data set for machine learning to mine, definitely.
Yeah, thanks, Sue. I mean, I guess you know, somewhere we always have to make have to take a shortcut, right? I mean, we cannot have the resolution necessarily we want. We can't have all the physics we necessarily desire to have, and of course, you know, machine learning is also taking shortcuts at some level. And I think what you're saying is a dynamic system that is you know, to actually solve the partial differential equations. Is going to be essential. I guess you know, I know that Jorge, for instance, had some ideas that you could have a sample of runs, ensemble runs, limited to running dynamical cores, and then on top of that, expand it with machine learning. So essentially, you start with maybe 50 ensemble runs that have the model that you want, that have all the physics that you want, but they are very costly, and then you sort of expand that with machine learning to 10,000 or 20,000 in order to reconstruct essentially your distribution function.
Another particularly possibly useful application here would as well is that a big challenge with weather at home is that you're using people's bandwidth, right? You're using their volunteered computing power and bandwidth and data storage as well. You have to save things before it gets transferred over. And so having something that can compress the data. And one thing right now with weather at home that we can't really do, I think, is feature tracking, but would be an obvious thing that it could be really good for. And so if you could add on some modules onto the model that runs on the person's computer and actively looks at the data and says, aha, there's a tropical cyclone moving there, and then comes up, measures various tropical cyclone measures, and that's what you get sent back. Or maybe it sends just a file about that tropical cyclone, which is the data about that, so it just suddenly turns on a pile of extra output. So you're not recording a whole pile of climate data when there's nothing interesting happening. But in particular, I think just being able to, these are the tropical cyclone tracks, this is their intensity. And those are sorts of things that feature tracking, which of course machine learning is kind of one of the best approaches, if not, certainly the most promising, I guess, to do, would be very useful. Peter, you're on the call, I think. Do you have anything else to add to that about the regional projections?
Yeah, I think those are both great points. The other one I'd add would be, for high resolution downscaling with machine learning, which is something we're looking into. So you could then go from, say, your 50-kilometer grid to a 1-kilometer grid potentially, by learning some of those transfer relationships. And perhaps combining that with some of the high resolution simulations we've done in the regional climate modeling group. So convective resolving simulations that are very high resolution, learning from those in a machine learning framework, sort of as an emulator, and then applying that, to get high resolution gridded output.
Thank you. We have another question that came from Paula Holland. The question is, thanks for the presentation, which was great. The lack of economics info or economic info for the assessments is a recognized problem. Did Treasury have any thoughts on a more structured approach to address this data problem? Is there a plan at all? Dáithí, Suzanne, sorry. Mm-hmm.
Go, Sue.
I was just thinking, I don't know, I think is the answer.
I mean, I don't think Treasury right now have any distinct plan, but Sue talked about this $12 million 5-year project that we're in right now, Whakaahura project. It's funded by one of the main government funding organizations here, MB. And part of that is not just improving our our understanding of extreme weather and climate models, building our climate modeling tools further and analyzing things more, but also looking at creating a disaster database, essentially, that records what sort of that links extreme weather with damages on the ground in terms of residential property and other factors. It's certainly residential property is the main focus because that tends to be where the data is best kept. But I think Elon's talking with the New Zealand Transport Authority as well. So looking at transport infrastructure and damage to that. So.
Thank you. The next question came from Alex again. Thanks for your answers. I'm wondering whether machine learning could also be used to uncover the economic impact and other highly nonlinear response functions. Dáithí, Suzanne.
Perhaps it gets one of the catches here that we're dealing with is that we're looking at extreme weather events. That's our focus, and extreme damage events, you could call them as well. And by their nature, they are rare. And so you have a problem with any sort of statistical tool, especially machine learning, that you are you have very little data to train with. So I could easily imagine something for more moderate events being built up. For the really big damaging events, it would be it's really hard to build these up because you hit thresholds. I mean, they're nonlinear, as you said, and so you hit thresholds where a levee suddenly breaks and suddenly there's flooding. It wouldn't have happened otherwise.
Thank you, Dáithí. There are no more questions in the chat box. I have a couple of questions that I would like to ask. First one is, we heard a lot about the distributed processing approach, but we didn't really hear much about where data is coming from. What is the data you use? Does it come from sensors, or it comes from satellites, or it comes from all possible sources one can think of?
Is that about the inputs? Do you mean the inputs to the models?
Yes, input to the models, yes.
Yeah. Ultimately, yes, all sorts of observations are used as input to the models. Weather at home is an atmosphere only model, so it's supplied with sea surface temperatures at its base, and it will also have values of greenhouse gases, ozone, aerosols. The full 3D atmosphere will be the initial state. Those will be taken from a variety of observations.
So yeah, right now with these simulations, it's just the ocean temperatures that are observed and put into the model, and I guess greenhouse gas concentrations. But there had been some thinking, I know, by the Weather at Home team some years ago, that maybe they could create a weather forecasting system with this, where they'd be able to produce a really large number of forecasts, and that would allow them to do a better job of catching those events that are really hard to forecast because they're very unlikely even in the forecast conditions. My understanding is that didn't really manage to work, and it comes down to the problem that you have to, because this is being run on people's home computers around the world, you would be having to send lots of data back and forth all the time, and that becomes really hard.
Thank you. My next question, again, I still don't see any raised hands on the floor, from the floor or on the floor, and I don't see new questions in the chat box. So my next question is about the models. We heard that you're using models for your modeling purposes, but we didn't really hear whether those models are homemade, I mean, or they're open source or commercial models, or, I mean, do you have special pipelines that you follow, and how's that organized?
Yes, I probably should have said a bit more about the model itself, but essentially Weather at Home is two models in one, and both of those are from the UK Met Office. So it's the global model had AM3P. So it's a global atmosphere at quarter resolution, which is about 150 kilometers. And then embedded inside that is the Met Office Hadley Centre RM3P regional model at 50 kilometer resolution. So they're both UK Met Office, based on what is now essentially quite an old version of the guts of the model, is a fairly old version of the and certainly I think the history of the project essentially is that it was initially hard enough to port that, to make that portable and downloadable, that the base model didn't change that much for quite a long time. That's now changing in the sense that CPDN is making available other types of more modern model, but Weather at Home is certainly still based on those two models. And although the guts of those are pretty old now, it's at the same time it's also a tried and tested and in many ways very good model. So I don't know if that helps, but certainly there are current developments afoot at CPDN to make other models, such as the ECMWF IFS model and the WRF model, Weather Research and Forecasting model. They're in the process of distributing those under this BOINC framework. So that will be an interesting development.
More generally, at the beginning there, the answer is a variety. Some of those are, I guess, all of the statistical downscaling can be entirely in-house. All of the other models that we use have been made originally abroad. Some of them we use off the shelf. Some of them have been augmented in some way, like NZESM that Johnny talked about a couple of weeks ago, which has been built in the UK, but which has people, Johnny and others at NIWA, have modified in certain ways to improve what it does in the New Zealand area. In terms of Weather at Home, they're always keen to look at other regions of the world. So they'd be very open to starting a project there, if that's of interest.
Thank you very much, and mindful of time, it's 2:02 now, and I'm about to finish this session. Before I ask the floor again, if there's any other questions to be asked now. Anyone? No? Dáithí and Susan, thank you very much for your time today. Thank you very much for your presentation, and of course, thanks to all of the members of the audience, and big thank you to the organizations like MFAT and DFAT for participating in this webinar series. I'm looking forward to see you again next Tuesday, when we will have GEM presenting their projects. I will send the invite in the next 15 to 20 minutes, and I'm looking forward to see you all there. Thank you very much again, and have a good day. Goodbye.
Thank
Thanks.
Thank you.
Bye.
Bye.